Okay, we've been talking about induced currents, and we talked specifically about if I take a wire and sweep it through a magnetic field, that's going to put a force on the charges in the wire and cause current to flow. But that's not really how we generally produce current. What we're going to learn about today is basically how all electrical power in the United States is created. And it uses this principle that when there is a change in flux, and remember, flux is the number of field lines. Current flows to resist the change. So I'm going to do a couple of examples. Let's say we do this example. We have a loop of wire, and we have a magnetic field in that wire that's going into the page. And we're going to change the flux. So we're going to turn off, in this case, the magnetic field. Okay, so when I do these types of problems, I have to first identify the change, then figure out how to resist that change, and then use that to figure out which way the current's going to flow. So the first step is to identify the change. Well, since I'm turning it off, the magnetic field is decreasing, the flux is going to decrease. So I have a decrease, and this flux is going into the page, so I have a decrease in the inward flux. To resist it, I have to do the opposite. So the opposite of decreasing in would be either decreasing out or increasing in. Now, I can't say increase out, because that's changing both of them, and it's kind of like a double negative. They kind of cancel each other out. So it's going to be decrease out or increase in. And I want to pick the one that's increase, because I can use that to figure out which way the current's going to go. So I'm going to say increase in. So the change was to decrease the in, the opposite, to resist it, I would increase the in. And that tells me, for my third right-hand rule, which way to point my thumb. Because I want to increase in inward magnetic field. In that third rule, my thumb goes in the direction of the magnetic field. So I want to increase the in. So this right here is telling me what to do. To increase the in, my thumb would point into the page, and my fingers would wrap around the loop this way. So that's clockwise. So I know my current would be clockwise in this case. So, if I turn off this magnetic field, suddenly current is going to start to flow clockwise around this loop. Let's do another example. Let's say I have a magnetic field this way pointing out. And I have a loop like this. Okay, and in this case, I will increase the area of the loop. I'm going to draw this a little bit different. So the magnetic field is very large and extends over a large area. If I increase the area of the loop, more of these lines are going to be inside the circle. So my change is to increase the number of lines, increase the flux, and those lines are pointing out. So my change is to increase the out. To resist it, I do the opposite. Okay, so the opposite would be either to increase in or decrease out, would be the opposite of increase out. And I'm going to pick the increase version. So I want to increase in. So this is telling me what to do with my thumb. I want my thumb to point into the page, and then my fingers wrap around clockwise. So in this case, the current would be clockwise as well. Now, another one I'm going to do real quick over here, I'm going to just, let's say I have a loop like this, and I'll have my magnetic field like so. And I'm going to draw in a little axis here. And what I'm going to do is spin the coil 90 degrees. So it's going to be like this. Okay, if I think of my fingers as being the flux, right now I have 5 fingers or 5 going through it. If I spin it 90 degrees, suddenly none are going through it. Okay, so that gives me a change in flux. And this is actually how we produce power almost everywhere. If you think of a coal-burning power plant. In a coal-burning power plant, they use the heat, they burn the coal, create heat, which boils water. The steam then expands and it gets forced through a turbine, which is like a big fan, and that spins a coil near a magnetic field. So as that coil spins, the flux is decreasing and then increasing and then decreasing, so it's continually changing, and as the flux changes, it's producing current. Same thing at in a nuclear power plant where we in Rochester get our power. You use the nuclear energy to boil water, send the water through send the steam through a turbine. Turbine spins a coil. Niagara Falls, they produce a lot of power. Hydroelectric. You take the water from the waterfalls as the water is rushing downward, spins a turbine, which spins a coil, changes the flux, and produces electricity. And virtually all of the ways that we produce energy use that. Windmill, same thing. The spinning of the windmill spins a coil. So we're going to spin the coil 90 degrees. If I spin it 90 degrees, I'm going to decrease this flux, which is pointing out. So that's my change. I need to resist it. So the opposite of decreasing out could be increasing out or decreasing in. I want to pick the increasing. So I'm going to increase the out. And in order to increase the out, I take my thumb and I point it out. My fingers curl around this way. That's going to be counterclockwise. So my current, in that case, would be counterclockwise. Now when I do these problems, every time I write change, resist, and what's happening with the current. If you don't want to show all the steps, you don't need to, but I think it helps keep things organized in your head. Now the math for this is going to be as follows. We can calculate the flux by doing B, A, cosine theta. The magnetic field times the area times the cosine of theta. So almost always you're not going to have to worry about the cosine of theta because all of the flux is going through the loop, so I don't have to worry anything about an angle. I would just do B times A. It's only when you have an angle in there you need to worry about it. Then the EMF, which we learned about last time, is going to equal N times the change in flux over the change in time, where N is the number of turns in the coil. On the reference table, it actually just says change in flux over time. They don't talk about the number of turns, but I like to because the more wrappings you have, the more wrappings of wire you have in your coil, the more voltage and the more current you're going to get out. So here's an example. Okay, a loop of wire has an area of 0.01 meters squared, a resistance of 2 milliohms. So we're going to say that this is our area. This is our resistance. Magnetic field, so there's B. Magnetic field shuts off, that's kind of important to know. Period of 0.01 seconds, so that's a time. And then I want to know the magnitude and direction of the current in the loop. So the first thing I'm going to do maybe is calculate the flux. So the flux is B, A. I'm not worried about cosine theta because all those lines which are pointing out of the field are going through the loop. So my magnetic field was 4, and my area was 0.01, and that's going to give me a flux of 0.04. Now for the unit for that, it's Webers or lines, but most of the time you'll see it this way. We got it by multiplying Tesla times meter squared, so Tesla meter squared. Then I can use this new equation. Curly E is N change in flux over change in time, and that's going to give me, it's just a single loop, so N is going to be 1. Alright, so I don't have to worry about it. The change in flux, well I had 0.04 flux, and I'm going to shut it off, so it's going to go down to 0, so my change in flux is going to be 0.04. and then divide that by the time of 0.1, and that's going to give me 0.4 for my curly E. And we have to remember, what is that? The EMF is the same thing as voltage, so it's going to give me 0.4 volts. I'm not quite done with the problem because it's not asking for my voltage, it's asking for the current. How are we going to find that? Well, we just found V, and we're probably going to use V equals IR. So we'll do V equals IR, 0.4 equals I times, the resistance was 2 milliohms, so 2 times 10 to the minus third, and my answer is going to be I equals 200 amps. Alright? Now, to finish this off, we want to find the direction of the current. So I do my change. My change was it's shutting off, so it's decreasing. And these dots mean it's pointing out of the page. To resist that change, I want to increase the out, because that would be the opposite. Alright, and that tells me which way to point my thumb to find the current. So I want to increase the out, so my thumb has to point out of the page, and my fingers are going to curl around this way, so that's counterclockwise. So the current is counterclockwise.